Hi, I'm Laure. I'm a faculty at NYU. I'm a climate dynamicist. I work mostly on the role of oceans in climate, and this is what I'm going to tell you about in the next 30 minutes. So a little bit of background. So here what we're looking at is a satellite image of our planet. And of course, what you can see is mostly blue. So we mostly see ocean. So the ocean covers 70% of the surface of the world. So they are a pretty big heat reservoir. Just to give you an idea, the top 3 meters of the ocean contains as much heat as the whole atmosphere. The top 50 meters of the ocean contain as much carbon as the whole atmosphere. So they are a very big reservoir of heat and carbon. They absorb a lot of the heat and carbon that we have in the climate system. So I'm going to come back to it in a bit. But they're also important because they don't just absorb that heat and carbon, they can move it around. They can move it around from one place to the next, from one region to the next. So this way, they can actually affect global climate by transporting massive amount of heat and carbon on over great distances on quite different type of timescales. So here, this picture, right, you can see a lot of blue, so you can see the ocean. You can see also some clouds on top of it. But if we actually look at kind of, snapshots of what the ocean looked like still from space, then here's a movie coming from satellite altimetry that actually measure the anomalies in sea surface height. So it's basically a satellite that goes over, multiple satellites actually that goes over the planet Earth, sends a radar pulse that bounces back, and we can measure the sea surface height anomalies. So it's a way for us to actually understand how, deviation in sea surface heights are happening as a function of time. So this movie starts in the early 90s when, again, the satellite era, so to speak, started, where we could actually get very accurate measurements of the ocean from space. So here, what we see is different type of features. So if we look here in the tropics, for example, you can see things that are relatively coherent, relatively large scale in terms of their spatial scales. And so they are basically manifestation of waves propagating across the tropics. So if you heard of El Nino or ENSO, they are very much a manifestation of those changes in the tropical Pacific. If you look at mid-latitude, whether it's a northern hemisphere or southern hemisphere, and you can see that actually the picture is a little bit different. You have a lot of those kind of small-scale features that are popping up and kind of intermittently rather than being coherent over large distances. Those are turbulence features, those are called eddies. They're quite important in actually mixing heat and carbon in those regions. And they're actually a manifestation, again, of the chaotic and non-linear nature of the ocean. So even though in a previous plot we saw something quite blue that looked very, homogeneous, the ocean actually has a lot of variability on a wide range of timescales, both spatial and temporal. And so that makes it quite exciting to actually understand. But we take a step back again and kind of almost think about our view of the ocean, as this kind of big blob of water that has, a great potential to actually take up heat. So most of the heat, being stored in the climate system ends up in the ocean. So as I mentioned before, right, top 3 meters of the ocean contain as much heat as the whole atmosphere. So let's try to think about it in a bit of a different way. We put greenhouse gases in the atmosphere, that means we're warming the temperature of the planet. Now, because the atmosphere does not have a large heat capacity, most of that excess energy is being absorbed in the ocean. And we can really quantify that. So this is excess energy in the climate system as a function of time, which you can see are different components of the climate system. So where it's blue, all the blue colors is the ocean. So that's the amount of energy change that the ocean is experiencing. And you can see it's most of it. Very little energy change in the ice, atmosphere, and land are happening. Very much, most of the heat end up in the ocean. It's actually more than 90% of the excess energy that end up in the ocean. Now, because, we're warming the planet and we're warming the ocean, then water expands. And so that means if we look now at changes in sea level, then about, a large chunk of it, about half of it, that's actually due to the fact that water is expanding. And so sea level goes up. Now, the other part is, again, because temperature is warmer, then we're melting some of the glaciers and ice sheets. And so that's another big contribution. So to recap, the ocean takes up a lot of heat because of that. sea level goes up because water is expanding, right? And also because we melting some of the ice. Now, if we look at where is the ocean taking up heat, so here's a reconstruction that we've created that goes back in time for 150 years. We try to actually understand where the ocean will absorb this excess energy. And so this movie, you can see really places where heat storage is changing. And so you can see a couple of things. The southern hemisphere really kind of start to lighten up. And so the reason for that is the Southern Ocean can take up a lot of heat due to, again, its own dynamics. The North Atlantic is another place where there's a lot of kind of activity in terms of heat being taken up. So again, Southern Ocean and North Atlantic are those regions where the ocean dynamics are very active and kind of act as the lungs of the climate system. So they can breathe in and out different tracers, heat, carbon, oxygen, and so on. So the ocean takes up heat and carbon and other tracers. It does that, again, at a given rate, but that rate is very much determined by what the ocean dynamics are doing. And it's happening, again, in some regions of the world. And the heat is not going to be stored in the, uniformly over the globe. And so those are important concepts, that the spatial pattern of heat uptake and therefore sea level rise is not uniform. So some places will experience actually more sea level than others. So this has big implication when we try to think about what might happen in the future. If we continue thinking about what has happened, again, picking a point where I am, which is New York City, here we can actually measure directly how sea level has been changing in Battery Park, so basically in the southern tip of Manhattan, as a function of time. So going back to the late 19th century. So what we can see here from tide gauges, so basically kind of a measurement of sea level, going up. And we can see basically almost a linear trend, right, over the entire period. There's a lot of variability, right? So there are a lot of spike kind of going up and down, which is to be expected. But overall, basically almost linear increase over time. If you look at the number, you could say, well, it's not very large, right? It's less than 3 millimeters per year overall. So, not something that you would feel, kind of is devastating Manhattan. But the problem is even a tiny amount of increase in global mean sea level in, again, coastal area means that the risk of flooding are increasing. So every time that there's a storm, every time there's more rainfall, the, accumulation of water on land, especially in low-lying areas, can actually be more dramatic. So increasing flooding risk goes with increasing global mean sea level. And so places like New York are definitely more prone to that, or will be prone. So far we've looked at the past, both globally and locally. Let's try to think about what might happen in the future. And so with the future, we still have data, but it's a different type of data. We can't go and just, measure things or have some information that we can combine. We have to rely on simulation. So here, what we're looking at is the amount of ocean warming, so it's going to be on the vertical axis, as a function of time. And we're going to compare what climate models are doing versus observations in the past, and then what might happen in the future. So the observations or reconstruction are those kind of green lines that you see here. And what we're doing with models is, again, we try to, basically take numerical simulators that mimic what the equations are telling us the world should be doing. And it's based on the laws of physics. Now, we usually have multiple climate models because they all built slightly differently, and I'm going to come back to it in the next part. And so here, it's an average of 30 different models. So it's state-of-the-art climate models. And kind of trying to actually figure out if they can basically reproduce the amount of warming in the past, 150 years. So that's that black line. That is the average of all the models. You can see that on average, compared to the observation, so the hybrid data set, it does a pretty good job. There is a spread. So the spread is this kind of shading that you see around it. And that tells you where the model disagree a little bit, right? So the closer they are, so the less shading you get, the more consistent the models are with one another, the more spread you get, the less consistent they are. But over the historical period, again, they're doing a decent job. Now, if you go into the future, then, the uncertainty is going to grow in terms of what the models will be doing. Now, it grows for two reasons. One of them is, it depends on us, right? How much greenhouse gases we're going to put into the atmosphere. And so that gives us different color lines. That's just basically an assumption that we're making by saying, okay, let's give, that amount of greenhouse gases or radiative forcing in the climate system. And so then we run the model forward. Now, again, we have 30 of them, so they all will produce something. So for a given color, which means a given emission scenario, we're still going to end up with basically 30 models, which are giving us a bit of a different answer, right? So they're kind of giving us a different answer, even though we are assuming they all receive the same forcing, the same greenhouse effect. So there is some uncertainty in the rate of global warming, even when you average over the planet. If you look a little closer and we look at the patterns now, then we'll see that this spread, this kind of uncertainty, those kind of discrepancies between the model is popping up, a little bit more, drastically in certain regions of the world. So here, if we look at the amount of warming, the climate models are predicting, so this would be a map giving us the average amount of warming across multiple models. And you can see, like we saw in the historical period, right, the Southern Ocean is taking up a lot of heat, and so is the North Atlantic. So in the future, it seems that the patterns of warming are still, very much behaving in the same way as in the past. Now, if we look at the spread, meaning how the models are diverging from one another, we can see that places like the North Atlantic, where there's a lot of expected warming, there's also a huge amount of spread, meaning that the models don't necessarily agree on the magnitude of the warming in those places. And you can see that, for example, along the US East Coast, we can get a lot of uncertainty, or again, along South America. So some places are going to experience, or at least are expected to experience, a large amount of warming, but how much, model give you different answers. And a lot of that comes to the fact that climate models are formulated a little bit differently from one another. And so that's what we're going to, get into now. So here is basically just an animation of a simulation, a numerical simulation run at JFEL in Princeton. So one of the, big modeling center in the world. And what you can see is basically an animation of the surface temperature. And you can see the grid on which the numerical simulations are solved. And here the grid is relatively high resolution. It's 10 kilometer by 10 kilometer. And you can see sea surface temperature in the simulation. So the simulation includes everything: the ocean, the atmosphere, the land, the sea ice, and so on and so forth. And so you can see the Gulf Stream detaching from the US East Coast. You can see a lot of those kind of turbulent features that we talked about when we looked at satellite altimetry. So really it can capture the richness of the ocean, or at least its turbulent behavior and turbulent dynamics in this kind of relatively high resolution climate simulation. And so those tools are, extremely important for us, because they are a window into understanding how the climate has changed in the past and how it will change in the future. And so here we're zooming in on the tropical Pacific, where we had those kind of big waves, which you'll recall from the satellite altimetry. And so again, the numerical simulation can do a lot of that as well. So really an immense tool for us to, understand the climate system. So how are we using them? Where do they start? Well, they usually start with the laws of physics. We're pretty lucky in the sense that we have a set of governing equations that actually dictate how things are evolving as a function of time. So the first equation is extremely complicated. It's called Navier-Stokes. It's basically Newton's law for fluids, and tells us how currents will change. But then we also have to conserve mass, heat, salt, and then we need to relate, temperature, salinity, so salt, to density as function of pressure. So we have a set of quite complicated nonlinear partial differential equations that we need to solve. And those equations actually apply to all the range of scales, all the range of motions in the ocean. And so that's actually pretty impressive. Those equations can describe the large scale, meaning, the large scale ocean currents that are driven by wind, that are driven by heating and cooling, changes in fresh water, and so on and so forth. And those are thousands of kilometers in scale, and they evolve relatively slowly. So again, as the ocean circulation kind of, moves things around, it'll take years, decades, and centuries to actually transport a large amount of heat. but they also work for more turbulent features, those that we actually saw in multiple movies, turbulent eddies in the mid-latitude, for example, that are really important in steering and mixing tracers. But again, same equation work all the way down to dissipation that are just a few meters scale. So you really need to solve this full range of scales if you want to understand the climate system, because those small scales affect the larger scale and vice versa. So that's kind of one of the important, stories here. Mixing does not happen just at small scale. As you actually mix different properties, you'll change their temperature, and you'll do that at a scale that is quite often larger than the small scale that you begin with. And so that's very important for climate. Small scale, changes actually can affect the large scale climate on longer time scale. Now, think about those equations. And if you want to use a climate model, what you're going to need to do is you're going to need to take those complicated equations and break them into pieces so then you can solve them on a computer. Now, there are different ways to actually discretize, what we call discretize the equation, meaning, breaking them into pieces. And the numerics involved definitely has an impact on your simulation, but, there's been a lot of work kind of working on that aspect. Now, let's try just a thought experiment. Let's try to assume we want to actually resolve every single scale in that diagram, so all the way down to the meter scale. So if I were trying to resolve and take boxes of 1 meter cube and make them evolve independently from one another to solve the governing equation, we'll end up with 10 to the 28 equations to solve just the motion dynamics. So it's absolutely intractable, right? So we cannot resolve all those scales. We don't have enough compute power. So what we often do is, we're going to truncate at a given scale. So we're going to stop here, roughly at this resolution, 10 to 100, and we want to be able to resolve a lot of that spectrum of scales, meaning we will have some errors in our climate models, and those errors are the ones that are actually giving us the spread in the projections as we move forward in time. And so that's kind of the important message here. So just to show you in picture what the effect of, truncating scales look like, 10 equations that we solve on a grid, but now the grid has different resolution. So this is the high resolution grid that we looked at before, and that now we're looking at the Antarctic Peninsula. Celsius surface temperature, and you see a lot of steering and mixing, a lot of turbulence features and filament. You can see this kind of current shooting off here. So this kind of turbulence, again, is going to mix temperature, kind of interact with the sea ice as well in that region, and will have a very big impact on heat and carbon uptake. If now you can't afford that grid because it's too computationally expensive, usually typical resolution of climate models are around here. So 40 kilometer or 100 kilometer horizontal resolution. And you can see that now the movies are actually looking more sluggish, right? They're a lot more viscous. They look like peanut butter rather than something really turbulent. And that means that part of the physics is actually not well resolved anymore. I mean that a lot of the mixing and steering is not directly resolved by the simulation. But what we do in general to try to make the physics of those models as good as if you were to resolve all the scales, or at least all the ones that you care about, is this problem of what we call parameterization. The way to represent everything that is not resolved on the grid box size of the climate model and come up with simple mathematical representation for it. And this is true not just for ocean processes that are turbulent and mixing that is happening within the ocean. It's true for things in the atmosphere as well, like clouds, turbulence, radiation. So all those things that are extremely important to actually understand the climate system and predict it are usually occurring at a scale that is below the resolution of climate model. And so really understanding it and understanding how to represent it has been a big challenge in climate modeling for decades. Usually the way it's been done, it's been mostly to empirically come up with relationship that will best describe how those processes happen. So if we think about mixing, then there are some simple mathematical operator, like a Laplacian, that will actually do just that. They will just mimic mixing over a certain amount of time. It can only depend on what you resolve in your grid box, but they'll have some coefficients that, hopefully try to mimic the effect of what you're doing or the rate at which you want to do it. But it's been mostly empirical. So what we've been thinking about in our group and really motivated by our work of, understanding the ocean on global scale in terms of how much heat and carbon they take up, but try to reinvent or reimagine the way we can tackle the representation of processes that are not resolved in climate models. So rather than empirically coming up with a relationship, why not simply ask the data? And the idea is to try to leverage AIs, to machine learning, to extract information from high-resolution simulation on what's missing from coarse resolution models. So what we're going to do is basically take data set that are relatively high resolution, quite often coming from simulation, and extract, all those turbulent features that are missing from coarse resolution model, and try to understand the impact on the large-scale fluids. And so really asking directly the data, what is missing from coarse resolution model, by directly using machine learning and machine learning algorithm, but combined with theory a little bit, and try to extract what's missing. So really the goal is to represent all those scales, all those turbulent features, their effect on the large-scale flow that is completely missing from coarse resolution simulation, but rather than representing it in a very ad hoc fashion, we directly extract that information from the data set using machine learning that will give us the best representation of that missing physics. So again, a way to kind of, imagine that is, I know that the current is going to accelerate or that the temperature is going to change. So that's what I have on the left-hand side here. And the climate model is going to tell me very well, based on my discretized equation, it's a certain acceleration. But I need to correct for that acceleration or that change in temperature based on the effect of this turbulence onto the large-scale component of the climate system. So really what we're doing is adding a force, adding an acceleration, adding, if you want, a temperature change to the climate models based on all the missing physics that the simulation doesn't have, but that we were able to extract from basically high fidelity simulation or high fidelity data. So that's been done for the atmosphere for, started quite some time ago in the late 90s, but kind of a new wave of paper came out in the late, basically, I guess, 2019, and especially kind of looking at cloud. Been working a lot on basically ocean processes, so turbulent mixing, both horizontal and vertical. And I'm going to show you just a couple of illustration of that. And so it's part of a large international collaboration across multiple institutions. So just to give you a little bit of a flavor, without going into the detail, is let's start with a high resolution simulation. This is a low resolution one, so you can see it's there are less pixels, and it's less turbulent, so basically a little bit more boring. The question is, what happens if we take this coarse resolution simulation and add, those representation of turbulence that are missing in this coarse resolution one? So here would be, the representation of the simulation after we implemented a traditional physics-based parameterization. So representation of the turbulence that is happening, just using a simple equation that is pretty much made up in a way. This is going to be the coarse resolution with a parameterization, so a representation of turbulence that is learned directly from data with what we call convolutional neural networks. So they're pretty kind of, extensive machine learning algorithm that can learn kind of spatial features directly from data with kind of spatial correlations. So you can see, again, you can barely see any difference, but if I were, just judging by eye, maybe there is more turbulence in the one that was enhanced with, data and AI that is quite complicated. Here's the exciting one, where rather than actually learning a super complicated relationship, which is usually what neural networks are doing, let's try to learn something that is simple. Still from the data, but now we ask the data to actually learn an equation directly, again, from the same data set as we learn these very, very complicated features. And that's pretty exciting, because now we're interrogating the data on what's the best mathematical representation for the missing turbulence in coarse resolution model. So we don't need to a priori decide what the expression should be. We just let the algorithm figure it out in a way. And so, again, if I look at all those kind of snapshots of, turbulence, well, they all look, equally good, right? Depends a little bit on how you want to think about it. Depending on the metrics, some of them do better than others. Now, what's an interesting test, right, is we learn on a certain type of data, but technically we're supposed to learn physics. So we're supposed to learn something about the internal dynamics of the system. So what happens if I take the same model, but change a little something in it, which is, for example, where I am on the planet, meaning the rotation rate. If I'm in the low latitude versus the high latitude, I feel the rotation of the planet a bit differently. And so here, what we do is we take the same simulation, change one parameter, and by changing that one tiny parameter, again, which is related to the rotation rate, we can form jets now. So now it's not as, kind of coherent, turbulent features. We have kind of elongated, sharp jets, but we still have some turbulence. That's the coarse resolution where the jet have kind of, almost vanished and disappeared. So what happened if we take all those representation of missing turbulence that we have and implement them in this coarse resolution model? So the hope is I can reproduce as good, jet simulation as I have at high resolution, but without a computational cost. If we look at all of our three cases, so the one that is physics-based does not look great, right? It looks like it hasn't made any difference. If we look at the one that actually has implemented a very complex, non-linear relationship that has actually hundreds of thousands of parameters to mimic the turbulence, actually makes the simulation worse. So we learn from data a super complicated relationship that worked well in a case, but does not generalize well at all in another. So almost breaks the simulation. However, if you look at our relatively sparse, simple model that we learn from data, so we learn an equation from data, we don't relearn it, we don't retune it, we plug it into, again, a slightly different simulation, then we improve quite drastically the outcome of the simulation. So here, why am I showing you all those plots? Well, I guess a few reasons. One, there's a lot of information in data, right? So we looked at patterns of warming, we looked at, sea level rise, and, you probably got to analyze a lot of that data as well. So, they tell us a lot about how the climate has changed on, global scale and how it might change in the future. But another way to kind of use and utilize data is to learn something we didn't know before. And here what we try to learn is multiscale interaction in the ocean and to use those relationships to improve coarse resolution simulation. And the reason for that is by improving coarse resolution simulation, we can actually improve our projections of climate. And this is, something quite new. It still remains to be tested at global scale. Here, I just showed you kind of images of simulation that are rather idealized, but we have simulation in global climate models now to actually show, the good and the bad of doing that, learning directly from data to improve climate simulation. So there's a lot of work to be done in this area, but it's a very exciting one. So, you're entering this kind of age of data plus AI in a way, where we can't do anything without it in a way. So the amount of data is huge. Not all of it is of great quality, by the way, but all of it actually teaches us something, either on what has happened in the past, what might happen in the future. And quite often the idea is how do you combine that to actually enhance knowledge? But not just knowledge, improving knowledge also means that we can take action with the knowledge base that we have. So here's kind of a schematic of our project M squared line where we try to take different type of data sets, some from high resolution simulation, some from observations, some from other type of systems that, combine model and observations. And we try to enhance our understanding of the different scales and the different processes that are occurring in the ocean and in the climate system as a whole, so we can actually improve climate models and potentially improve projections. So this is really, a theme that is everywhere now. We have been, analyzing data for many, many years. The way we process this data now is very different. There is, almost no way that one can, not use data, for one project or another. And the way we're doing it these days is a little bit of the old school way where we still, plot and look at it to get a feel, but also, use kind of advanced algorithm to extract information in a way we never thought would be possible before. So there are quite a few projects going on. So LEAP, for example, is a science and technology center that also kind of, in the same vein of combining data, AI, to improve climate models, is also, basically thinking about different components of the Earth system. Of course, digital twins and digital Earths are another way to approach the problem where, quite often there's a lot of, high resolution simulation that are enhanced with data. So this kind of flavor of, numerical simulation data to improve climate model with AI quite often is for sure the future. So hopefully here you get a little bit of a flavor of how we came, to this. So, understanding the ocean across a wide range of scales, and really kind of combining AI and data with numerical simulators to better understand and predict climate. So I hope this gives you a bit of an idea of the type of work we've been doing, and you find some, inspiration as you start digging into your own data set. Thank you very much.